In this lesson, we will discuss the logistic regression modeling process and how it relates to neural networks. A second type of model that is commonly used in statistics is called logistic regression. With this type of modeling process, the goal is to create a model for prediction of a binary output variable using one or more input variables. Just like with linear regression, these input variables can be either quantitative or categorical. In fact, the whole process is done almost exactly the same as with ordinary least squares, but the parameter values are identified by minimizing the squared error equation on a transformation of the linear regression equation, which is done to ensure that we obtain probability values between 0 and 1. By having this restriction, we have a probability that the given individual belongs to one category over another, something that the linear regression equation does not guarantee us. The transformation that is done is on the screen. You can see that we're exponentiating the regression equation in the numerator of this formula and then dividing it by 1 plus the exponentiation of the regression equation. This is sometimes referred to as a logit transformation in statistics or a sigmoid function in mathematics and machine learning. Let's take a look at a motivating example for this type of model. Suppose that we want to predict if a tumor is cancerous or not. In this case, our output variable is a binary response. The tumor is either cancerous or it's not. We would like to be able to come up with a model that predicts whether a future tumor is cancerous or not, with the best available process being one that provides a probability of a tumor being cancerous. We have several measurements about the tumor that will be used as our input variables. As we did in the previous video, we first need to upload our data into Python. The data is in a text file, so the process to upload it into Colab is a bit different. Review the code on the screen to properly upload the data into your Python environment. Now we add a step to our modeling process. In particular, we're going to split the available data between a training and testing data set. We do this through the train test split function in the scikit-learn model selection package. Note in the code that there are 3 inputs to this function. The first is the data frame that we wish to split. The second is the test size. In this case, I'm requesting that 30% of the dataset be allocated to the testing dataset, while the other 70% will go to the training data. Finally, the random state function input is a seed for the data split. This allows you to get the same split if you were to run this function again in the future. I happen to pick a seed of 10 here, but you're free to use any value that you wish. A training data set is used to help us determine the best possible values for the parameters that we're using in our model. Just as we did before, we will find the optimal set of parameters by minimizing our mean squared error. But a problem could arise from this situation if we're not careful. If you look at the data provided on the screen, we have 9 input variables that we could potentially use to predict the classification of the tumor. What if one of these variables isn't actually helpful in prediction? If we tell Python to use a variable from this set to predict the classification, it will minimize the error using all of the available data, even if that data isn't particularly useful. This leaves us vulnerable to overfitting our model. What does that mean? Let's suppose we had a 10th input variable here, the number of dogs that a person owns. It's very unlikely that the number of dogs that a person owns will impact the status of the tumor that we're trying to classify. But if we put that variable in the model, then the software will try to fit the model to include that information. In essence, what happens is that the model will overfit the data we're currently working with and won't necessarily do a good job for predictions on future data, which is the whole purpose of using this process. To help account for this, we use a second data set, called a testing set, that verifies the solution we're finding with our training data set. We use the model that was created with the training data set to predict for the testing set and see how well our model fits the new data. Some variables may be removed or weighed less heavily after we see how the two results compare. The diagram on the screen demonstrates this concept and others that are closely related. Let's suppose we have only one or two input variables in our model. It is likely that in both of the training and testing data sets, we will have relatively high error rates because our model will not do a very good job at predictions with so few input variables. We call this underfitting the model. However, in the case that we just discussed, if we create a model that perfectly fits the training data set by using too many variables, or as we will see later, training a neural network for too long, then we will have low training error but high testing error. We call this overfitting our model. We are looking for a balance between the two of these things. We want to get relatively low training and testing error in our modeling process, which means we need to think carefully about the variables that we want to put in our model and not let our networks train for too long. Fortunately, with neural networks, we can let the computer decide when a variable isn't really helpful to the modeling process, and we can monitor the error rates for the testing and training data sets to make sure they both reach and stay at relatively low values throughout the modeling process. Now that we have and know why we need training and testing data sets, we can conduct our logistic regression modeling process. We will need to import the logit function from the stats model formula API package. Very similar to how we modeled our ordinary least squares or OLS regression equation, we can use this logit function with the formula for our model and the data that we plan to use as functional inputs. Note that in this first model, I'm using all of the input variables from the data set in the original model. Once I've defined my model, I fit and then print the summary. Just as we saw for linear regression, we're interested in the coefficients provided in the output to help with predictions. While the other information in the output has its own meaning in statistics, we won't worry about their interpretations here. To demonstrate the concept of overfitting, 3 of the variables from the original model were removed from the regression equation: epith, n-nucleus, and u-size. The output from the second model is provided on the screen. Using the scikit-learn metrics package, the mean squared error function was loaded into the Python environment. This was used to find the mean squared error for both of our models, comparing predictions from our model to the actual value from the data. In particular, though, we want to find the mean squared error for both the training and testing data sets that were created. Note that for categorical data, using the MSE is not the best metric for optimization and is used here as an example to demonstrate the current concept. We will look at better methods for optimization later on. To ease the computational process, the predict function for each model object was used to help find predictions. By default, the predict function will use the original data for model training to find predictions, or in our case, the training data. If we want to make predictions for a different set of data, we need to specify that in the predict function call. This is why in the second and fourth MSE calculations on the screen, the WBCA testing data set was the input into the predict function. It would not be incorrect to input the WBCA training data into the function for the first and third calculations on the screen, but as we can see, it's not necessary to do so. What we see here is that the mean squared error for our first model is smaller than the mean squared error for the second model when using the training data. Remember that our goal in this process is to reduce the mean squared error by using calculus methods and by adding and removing variables. If we were to just consider the training data set, the first model would be better for our purposes. However, a second mean squared error was calculated for each model using the testing data. And if we look at the results of those two metrics, we can see that the MSE for the second model is smaller, indicating that the second model may be better. While this isn't definitive proof, this output might tell us that the modeling process that includes all of the available variables is going to create an overfit model, that will do a really good job of predicting for the data that we have available to us, but it might not do such a good job of predicting in the future. We will learn techniques when we start creating our neural networks to avoid overfitting in our modeling process.